Okay guys, so this is segment 2, video 2 from the kinematics review. So last thing we need to talk about within the kinematics unit is constant acceleration. Usually when we're dealing with constant acceleration on the AP exam, it's due to an object either in free fall or projectile motion. So what that means is that the object is accelerating at a constant rate. That constant acceleration is caused by a planet's gravitational field. In the instance of Earth, right, all objects near the surface will undergo the same acceleration as long as there's no air resistance. Okay, and in most of the cases that, actually in every case we look at in AP Physics 1, there is no air resistance. Technically, we know that objects accelerate at 9.8 meters per second squared. On the AP exam, if they do give you numbers, they're going to tell you to use 10. What will most often be the case determining the changes for this year is that they'll ask you for conceptual relationships. We actually looked at a problem in the kinematics unit in which you had to conceptually explain information about the object's velocity and position at given times when it was launched at an angle. So that was a practice open-ended question that we did before the review, so you might actually want to go back in your notes and take a look at that if you get a chance. So we're going to start with constant acceleration first in one dimension, and then we'll head to 2 dimensions. So if an object's accelerating at a constant rate in one dimension, we call that free fall. Right? So in free fall, an object is either dropped from rest and moves along a straight path in one direction only, is thrown vertically downward, which still moves along a linear path in one direction, or it's thrown vertically up, which means that it vertically moves straight up and then comes straight down along the same path, but it's moving in 2 different directions, up and down, but within the same dimension. Some shortcuts, right? When we know an object is dropped from rest, we know that means that the initial velocity is 0. When we're talking about free fall and projectile motion, we assume that down means positive. So the acceleration is positive 10 meters per second squared. If you are described a situation in which an object is thrown vertically down, that means that the initial velocity is greater than 0. Okay, so it starts at a velocity that's greater than 0, it's thrown down, we assign down to be positive, acceleration remains 10 meters per second squared. If an object is thrown vertically upward, right, that opposes the force of gravity, so the initial velocity is going to be negative. Okay, it's going to be negative and a value greater than 0. So what that means is that the initial velocity is less than 0 technically, because that value would be negative, meaning opposite to the direction of the force of gravity. We also say that the acceleration is negative because at first the object moves upward. As it moves up, it's going to begin to slow down, right? If you remember, direction of acceleration and direction of velocity. Technically, it's going to slow down until it reaches maximum height, where it'll find a velocity of 0, and then it'll speed up as it moves towards the ground. When we're solving free fall questions, we use the big 4 equations in one dimension. Okay, so we use the big 4 not in terms of x and y, which are listed there below. Your AP exams open notes, so you can actually use this document if you'd like to, or you can use your note card so you don't have to worry about locating them on the formula sheet for the exam. Some quick tips about interpreting word problems, right? If an object starts at rest, that means the initial velocity is 0. If the problem states the object comes to rest or stop, then the final velocity is 0. The final velocity of a falling object just before it hits the ground is not 0. You cannot assume that the final velocity of any object is 0 unless the problem specifically states that the object comes to a rest or comes to a stop, if those words are not in the problem, the object's final velocity is not 0. So for projectile motion and free fall, the final velocity is never 0. Okay, not in the x, not in the y. If the problem states that the object moves with a constant velocity, that means that there's no acceleration rate. Right? Acceleration is the change in the velocity over the change in time. If there is no velocity change, then there's no acceleration. Okay, if you're told that the object is in free fall, it's dropped from rest, it's thrown vertically upward, launched at an angle, launched horizontally, with no value of a mention, no mention of a value for the acceleration due to gravity, you use 10 meters per second squared. Okay, so let's head into two-dimensional constant acceleration. When an object accelerates at a constant rate in the y, okay, but it also has motion in the x, we call that projectile motion. So we're going to look at constant acceleration when there's motion in two dimensions. Specifically, we broke it down into two different types of motion, which are defined here for you. So horizontal launch is when an object is launched with the horizontal, aka it's launched off of a flat surface or a table. It begins at the maximum height. That path of motion, right, is half a parabola. So it's half a parabolic path. It begins at its maximum height. The assumptions that we make here are that the y component of the initial velocity is 0, but it only has velocity initially in the x. It has no component to the y velocity because it's launched horizontally. The x component, however, will be constant throughout the entire path of motion because there is no acceleration in the x. If there's no air resistance, there's no force in the x direction to cause an acceleration. So that initial velocity in the x will be the x component of the velocity throughout its entire path of motion. The y component, although it starts at 0, it will change due to this positive acceleration rate. So for each second that it's in the air, the velocity is going to increase by 10 meters per second. Typically in these problems, we might not use this exact equation to find the exact variable listed, but we'll use that equation to find a variable that is missing. So basically here, we might not specifically want to find time, but if we know the maximum height, we can find the time. Okay, technically we know the initial velocity in the y is 0, so that entire quantity becomes 0. 0 times t will be 0. So we can find time, which is the same in both the x and the y, using the height of the table or the surface and our value for a sub y, which should be 10 meters per second squared. Next up, we find the range using the range equation. Remember, there is no acceleration in the x, so this entire portion of the equation cancels out. 0 times anything is 0. To find the final velocity, if we were asked for it, we have to find both the x and the y components to the final velocity. Remember, it is not 0. So this vector here has both an x and a y component. To find the x component, we know that it must be constant. So the initial velocity in the x is the x component of the final velocity as well, because there is no acceleration in the x direction. In the y direction, however, there will be a change in the velocity. We have to calculate it. So the final component of the velocity in the y will be equal to initial velocity in the y squared, which we know is 0, so that whole quantity cancels out, plus 2 times positive 10 meters per second squared times the height, the starting height. Once we find the x and the y components, we can use Pythagorean theorem to find the magnitude of the velocity if we are asked for it. With non-horizontal launch, the maximum height is technically the starting height. So we don't actually need an equation to solve for that. We're usually given that value, delta y. Okay, next up we have non-horizontal launch, which means that the object is launched at an angle with the horizontal. It has two components to its displacement, two components to the velocity, and two components to the acceleration. So our first step, right, if we're talking about non-horizontal launch, the object is launched at an angle with the horizontal. So we must find the x and the y component to the initial velocity. We find that using what we know about vectors and their components. So we use trig to find the x component of the initial velocity. We take the initial velocity and we multiply by the cosine of theta to find the x component. To find the y component, we take the magnitude of the initial velocity and we multiply by the sine of theta to find the y component. After we've broken the velocities into x and y components, right, we know our delta x value, etc. We will find the time because it's the same in both dimensions and it's useful in problem solving. So we're going to take delta y. We'll take that third equation in terms of y variables. Delta y equals VO in the y times t plus 1/2 a in the y t squared. Delta y, right, if it starts and ends at the same height, the change in the height will be 0. So we should plug in 0 here. If the change in the height is not 0, use your calculator, use solver, okay, to figure out the time. Okay, but in most cases it will be 0. The initial velocity in the y we solve for in the first step. Please make sure that you do not plug in the magnitude of the initial velocity. That's one of the biggest mistakes. It's the y component of the initial velocity. So it's the magnitude times the sine of theta times t, which we don't know, so we leave that as a variable, plus 1/2 times acceleration, the y is 10, times t squared. When this is set equal to 0, we can easily manipulate the equation for t. When delta y is not 0, then we have to use quadratic formula. Okay, next step is the same as horizontal launch. We find the range using the x component of the initial velocity and the time in which we solved for in the previous step to find range. Or if we don't know initial velocity, we can use range and time to find the initial velocity. Last step, to find maximum height, we use big 4 equation 2 in terms of y variables. We have v in the y squared equals v initial in the y squared plus 2 times a times delta y. And that delta y is that maximum height. At the maximum height, the velocity in the y is equal to 0, right? The object's velocity decreases until it hits its max point. At its max point, its velocity increases due to the acceleration rate until it hits the ground. So this initial velocity here will be equal to 0 every time. This final velocity here will be equal to 0 every time. The initial velocity in the y we already solved for in the first step. We know acceleration is negative 10 meters per second squared. Negative because we're opposing the force of gravity. And then we solve for our maximum height. Okay, last thing, graphically, in which up here under review examples, there's 2 open-ended questions. These open-ended questions resemble practice AP exams. So the links are here, and I'll also post the answer keys. So being able to graph your position versus time, velocity versus time, and acceleration versus time is very useful and will most likely be on the open-ended section. So if we consider here It's a little bit blurry than I'd like. So I'm going to make it a little bit larger, and then I'll shrink it so it fits back on your document. We consider dropping an object from a height of 2 meters above the ground. Okay, we know that the acceleration will be a constant value of 9.8. If it's dropped, that means that the initial velocity is 0. So our position versus time graph, right? Actually, it's probably easier to start with our acceleration versus time, so let's go there. So our acceleration versus time graph, we know acceleration is a constant rate. Why is this not working? Okay, that's better. So acceleration versus time we know is a constant value. Constant on a graph, right, is a horizontal line. So we should have a horizontal line at negative 9.8 or negative 10, according to AP College of War standards, meters per second squared. So you know the acceleration is constant. To find the velocity, we could take the area underneath the curve. This area will give us the velocity, which we know will be a linear line in the form y equals mx plus b, where the slope of this line is equal to the acceleration. Okay, because we have rise, which is a change in velocity, over run, which is a change in time, which is quite literally the definition of acceleration. So the slope of this linear line should be negative 10. The y-intercept is 0, 0, because the velocity begins at 0 when time is 0. If we take the area between the x-axis and our velocity trend line, we can determine the position versus time graph. Okay, so technically in our ticker timer lab, right, we drew tangent lines and took the slopes of the tangent lines to create a velocity versus time graph. Okay, we know that if acceleration is constant, that position will increase or decrease at an increasing or decreasing rate. In this case, if we say that the position begins at 2, we'll see here that the slope of this segment is almost 0. The slope is going to increase over each second until our object hits the ground. So basically, our slope is increasing in the negative direction. So we have a concave down parabolic curve that starts at a position of 2 and ends at a position of 0. Okay, so those are what our graphs are going to look like for projectile motion. Okay, to go from position to velocity, we take the slope of the tangent lines. If it's a parabolic curve, okay? If it's not a parabolic curve, we can just take the slope of the linear line, and that slope will be equal to the acceleration. So to go from position to velocity to acceleration, we take slopes. To go in the opposite order, right, to go from acceleration to velocity, we take the area between the trend line and the x-axis, which in common language we say the area under the curve. But technically, right, in the case of a negative velocity, it'd be the area above the curve. Okay, so to go in the opposite order, we take the area. Okay, so from position to velocity to acceleration, we take the slope. To go from acceleration to velocity to position, we take the area above or below the trend line. So we take the area between the x-axis and our trend line. Okay, so that's it for kinematics. Stay tuned for the next set of review videos. And please check out these two open-ended practice problems, okay, they're really good manifestations of kinematics in an open-ended problem, so qualitative to quantitative justification, and then the paragraph response. So there's an example of both types for kinematics that might be on the AP exam.